Hello, welcome everyone. Today for metal mediated synthesis, we will discuss transition metal carbenes. As you all know, carbenes are divalent carbon centers with two atoms attached to with it. Transition metal carbenes are the one where metal is associated with the carbon center and the carbon is attached with two different atoms. Today we will discuss the transition metal carbenes, how they are synthesized, how their names has appeared and also their reactivity pattern. Let us look at the transition metal carbene. What are those actually? So, transition metal carbenes are the one where metal is doubly coordinated with a carbon center and the carbon center is attached with A and B, two different atoms. Now, general classes typically features two types of carbene, as you know, Fischer Carbene and the Stock Carbene. These two types of carbene we have very distinct features. Fischer carbenes are electrophilic at the carbon center and the Stock carbene are nucleophilic at the carbon center. In addition, there are a number of characteristic features that differentiate the Fischer carbene from the Stock carbene. Let us look at one example of Fischer carbene and point out the characteristic of such carbene compound. Subsequently, we will discuss the Stock carbene with one example and their characteristic features. Let us try to look at Fischer carbene. So, Fischer carbene. Well, first of all, it is easier if we try to remember one example of the Fischer carbene and one example of the Stock carbene. So, with one example we will try to discuss their inherent properties and the type of ligand that is associated with the metal center. One example that you might want to remember for the Fischer carbene is the one where you have the chromium complex. Let us look at the characteristic features. So, the chromium complex is associated with the carbene center with two atoms associated with the carbon center and this is a pentacarbonyl species. Now, if you look at this chromium complex very carefully, the chromium center is attached with some ligand and the carbon center is also attached with some substituent. Now, let us look at each of these features quite carefully. The chromium center, as you have seen, is associated with carbon monoxide. Now, these are the ones which are going to be your pi acceptor type of ligand. On the other hand, the carbon center is electrophilic in nature as you see in the chromium complex. Let us look at the characteristics one more time and carefully. So, you have chromium complex with pentacarbonyl associated with it. The carbon center over here that is electrophilic in nature. This is electrophilic in nature. In a moment we will see the Stock carbene is nucleophilic in nature. Usually the metal center that is associated over here is the middle or late transition metal and these are having lower oxidation state. So, lower oxidation state and transition metals are late or middle. These are the characteristics of your Fischer carbene. Most importantly, you have pi acceptor ligands. These are the one, the carbon monoxide are the one associated with the metal center directly, which are pi acceptor in nature. On pi acceptor ligands on transition metals, that is, for example, you have carbon monoxide in this particular case. And the two atom that is associated with the carbon center, they are often a pi donor. A and B are often pi donor. Okay. So, these are of two different types. Usually we can get alkoxide or Nr2 type. So, as you have seen with the Fischer carbene, this is an example of a Fischer carbene where you have chromium complex of pentacarbonyl species and the methoxide and phenyl is attached with the carbon carbene center. Now, chromium is directly associated with a pi acceptor ligand. The carbon center, the carbene carbon center is associated with and the L type ligand, which is the pi donor ligand. That means the methoxy you have or Nr2, anything you can have, these are going to be electron donating in nature. And therefore, the carbene carbon center is electrophilic in nature. You can draw a conjugation between the lone pair of the methoxy and to that of the carbene double bond. So, the carbon center at carbene is electrophilic in nature. That is most important feature of the Fischer carbene. You have chromium complex over here, you can have other middle or late transition metal complexes. Once again, the main features you need to look at is whether carbene carbon is electrophilic or nucleophilic in nature. If it is electrophilic in nature, it is going to be Fischer carbene. The atoms, two atoms that are associated with the carbene center, that is going to be at least L type of donor, that is it is the lone pair is there on those hetero atoms. Okay, let us look at one example of the Fischer carbene. So, Fischer carbene we have looked at, now let us look at the Strock carbene. These are the ones also alkylidine type of molecules. Okay. We can have a tantalum complex with neopentyl 3 and the classical this carbon center with the carbene. Now, this carbene, as you will see, this is delta negative. Neopentyl are the one where you have CH2 tert-butyl group associated with it. Okay. This is your neopentyl group. Now, this compound, if you look at, we have a higher oxidation state for the transition metal. In case of Fischer carbene, this one was a lower oxidation state for the metal. Now, you have a higher oxidation state of the metal. In this particular case, this is tantalum 5 plus. The carbon center, the carbene carbon center is nucleophilic in nature. So, the most importantly, it is going to be nucleophilic as opposed to the electrophilic Fischer carbene center. Nucleophilic at carbon, and you have higher oxidation state. Tantalum, as you can see over here, it is +5 oxidation state. So, higher oxidation state as opposed to Fischer carbene, where usually it is a lower or middle oxidation state. Transition metal in this Strock carbene, these are earlier transition metal in nature. And most importantly, you see the metal center is not associated with something which are pi acceptor in nature. This is not a pi acceptor ligand, unlike carbon monoxide. So, non-pi acceptor ligand is directly attached with the metal center, non-pi acceptor ligand. This is very characteristics of your Strock carbene, and the two atoms that is attached with this carbon center, the carbene carbon center, they are not also pi donor. So, non-pi acceptor, non-pi donor type of complex will give you the Strock carbene. The A and B are not pi donors. Usually these are the ones which are X2 type of ligand. So, these two carbenes we have discussed with one example are very characteristic, and their synthesis pattern is also very different. Fischer carbene and Strock carbene are the two different type of carbene you can expect. Therefore, the reactivity of these two carbenes are also varying. For Fischer carbene, we have seen the carbon center is electrophilic in nature, or the carbon you can think of delta plus. For the Strock carbene, we have delta minus at the carbon center. For the Fischer carbene, the metal centers are the one which are middle or late transition metal. The metal center is also associated with a pi acceptor type ligand. The carbon center of the Fischer carbene is attached with two different atoms. If it is A and B, none of both of them, or at least one of them, should be pi donor in nature. This leaves the carbon center electrophilic in their characteristic. On the other hand, for the Strock carbene, you have the carbene center nucleophilic in nature, that is delta negative. Most importantly, A and B that is associated with the carbon center are not a pi donor. The other ligand that is associated with the metal center is also not pi acceptor type. Therefore, as you can see, the metal center that is associated for Strock carbene is the earlier transition metal ones, and their oxidation state is relatively high compared to the Fischer carbene ones. All right. Now, let us look at the synthesis of these two different type of carbene, namely Fischer carbene and the Strock carbene. First, we will discuss the synthesis of Fischer carbene. So, we can start with a chromium hexacarbonyl species. Okay. We have, let us say, one carbon monoxide we are putting on the outside. Now, this phenyl lithium will react with one of those carbonyl center to give you CO5 chromium phenyl species, right. From there on, we can have, so this is the species which is the usual carbene you can think of, chromium double bond and O minus phenyl species, right. From there on, if we have reacted with, let us say for example diazomethane, we will get chromium, this usual Fischer Carbene complex, where we have a pi donor type of ligand, and pentacarbonyl is associated with the chromium species. Most importantly, this compound you can write down in a canonical form, where you have minus and plus center at the carbon in the carbene center. Overall, you can write down as if the chromium is minus and OMe is OMe is plus in nature. Okay. So, as you have in this synthesis, what we have done is simply we have taken hexacarbonyl chromium complex and reacted it with the organolithium reagent PHLi in this particular case. Now, this organolithium reagent has reacted with one of the carbon monoxide center to give rise to an intermediate from which you can react with diazomethane to get your Fischer Carbene species. This is a very easy synthesis, and of course, you need to handle it little carefully, but overall it is relatively easier synthesis. So, that is one of the synthesis for the Fischer Carbene. Now, we will look at one of the synthesis of Schrock Carbene. So, Schrock Carbene was not really a planned synthesis. It was Richard Schrock when he was at DuPont. He was trying to synthesize a different complex, we will come in a moment, but accidentally he has discovered a very interesting complex, which then later came to fame and known as Schrock Carbene. It is the tantalum complex that was studied at that point at DuPont by Richard Schrock, where we will see the accidental synthesis that has revolutionized this area of organometallic complexes and subsequent chemistry to give the metathesis reactions. Now, Schrock Carbene. It was discovered in 1974. Once again, Richard Schrock was at that point at DuPont scientist. Later on he moved to, of course, as right now he is at MIT. Before that he was at DuPont. So, neopentyl 3 tantalum chloride complex he was studying, and he was interested in reacting with lithium neopentyl complex. The idea was to get NP5 tantalum complex. Instead, what he actually got is a history, and that is neopentyl TA3 instead of pentaneopentyl tantalum complex, he got this tris neopentyl tantalum complex with the carbene center attached with the tantalum. Of course, tantalum is in 5 oxidation state. Similar reagent one can think of that can have this type of behavior, or similar behavior as Schrock Carbene could be your Tebes reagent, where this Cp2 titanium can be attached with aluminum, and overall you can have a reaction where this is Cp2 titanium double bond, okay, or carbene center. Most often nowadays the one carbene or Schrock Carbene that mostly people familiar with are the one with the molybdenum complex, where this molybdenum is in +6 oxidation state, and alkylidin we have this counterpart where this isopropyl and 2 isopropyls are associated with this amine center, and your metal is associated with 2 alkoxide, where R, this alkoxide R is CMeCF32. So, this is the modern day Schrock catalyst, where Schrock Carbene, as you see, was first discovered, although accidentally, in 1974 at DuPont, where pentaneopentyl tantalum complex was planned to synthesize starting from the tris neopentyl tantalum dichloride species by reacting with neopentyl chloride. Unfortunately, or I would say rather fortunately, we did not see the synthesis of, or we did not get the tris from the tris neopentyl species to pentaneopentyl tantalum species. Instead, what we ended up getting is the one of the neopentyl of the neopentyl lithium reacting with the tantalum dichloride to give the tantalum 4 neopentyl species. The 5th neopentyl one abstract from the alpha carbon CH bond to give the neopentyl 3 of them on the tantalum, and the other one is now associated with the tantalum center in a double bond or so called Schrock Carbene fashion. Now, this was the initial discovery. Till then numerous progress has been made. The one with which we are mostly familiar with as a Strock carbene are the one we have molybdenum complex. Molybdenum is in +6 oxidation state. As you have seen, we have the nitrogen associated with the molybdenum, and these two diisopropyls are bulky substituent on this amine, and we have the carbene center right over here, where this is nucleophilic in nature, and as you have seen, there is no pi acceptor or pi donor ligand in the whole complex. We have the alkoxide complex, where R is again a bulky one, tertiary carbon center with CmECF32. Another carbene which you are often familiar with is the one which is most popular, I would say at this point, that is the Grubbs one. Okay. As you look at when Grubbs started out his career, he did not have his carbene to start with the reactivity. He was initially working with the Strock carbene. Later on, he came up with a very modified and versatile version of the carbene, which came to fame as the Grubbs catalyst, as you know it, and there are different generations of the Grubbs catalyst that we have in the market. Now, the one in the Grubbs catalyst we need to discuss, that is the one which is most popular. We have this Ruthenium complex. Once again, this is of Strock carbene type, where you have ruthenium attached with the carbon center. This is again nucleophilic in nature, and you have PCY3 dichloro species attached with it, and two of them, sorry, PCY3. So, this is the one which is known as Grubbs, and this was first discovered in 1993, and you have of course different other ligands are also used for this Grubbs catalyst. Now, as you know, this is the Strock carbene covers also the Grubbs this catalyst, because this carbon center is nucleophilic in nature. As you have seen, first example was in 1974, and later on Grubbs comes at 1993 to come up with his own modified and the very reactive version of the Strock carbene, which is known to the literature as Grubbs catalyst or Grubbs different generation of catalyst. Later on, as you know, both of them came and developed this field quite beautifully to give the field the prominence, and nowadays the organic synthesis or even any synthetic chemist cannot think of doing a complicated molecule synthesis without utilizing the great nature or great behavior of these two carbene complexes. We will now look at little bit at their reactivity pattern. So, we will look at the application of this, specifically the Fischer carbene and the Strock carbene. First, we will discuss the one where we have the metathesis reactions. So, we will have two important carbon-carbon bond formation process that will go on for the metathesis reaction. If you start with one olefin where two different substituents are there, let us say R and R, and you have another olefin where once again two different substituents are there, R prime and R prime. Now, if you react it with the Strock carbene, or so to speak nowadays Grubbs catalyst or Strock catalyst or Strock carbene, usually you will get an exchange of partner where one half of the olefin will be exchanged with the another half to give you the mixture of this compound, the final compound, where one half is associated with the double bond of one carbon or of one olefin, the other half is associated with the other olefin. Now, this metal is used as a catalyst and often it is done under thermal reaction control. Of course, it can be reversible in nature. These carbon-carbon double bond, as you know, these are 150 kcal per mole, and doing this reaction, breaking and doing these reactions are quite interesting, because you are breaking a 150 kcal per mole, that those compounds with the double bond in there, and you are exchanging the partners at room temperature. How these reactions are possible at room temperature has got the imagination of the whole chemistry community. This is because the very reactive nature of the carbene that helps them to undergo a 2+2 reaction first. We will see in the latter next class, where 2+2 reaction first and then a retro 2+2 eventually gives an intermediate which leads to the final product. So, for this class what we have seen so far is the two most prominent or the two known classes of carbene, namely Fischer carbene and Strock carbene. With one example is we have tried to show the characteristic feature of both these carbenes, Fischer carbene and the Strock carbene. As you have seen, Fischer carbene carbon center is electrophilic in nature and Strock carbene carbon center is nucleophilic in nature. Their synthesis you have seen also are of different in nature. You have chromium hexacarbonyl species, for example, to start with, which was reacted with phenyl lithium to give you the Fischer carbene. On the other hand, Strock carbene, which was discovered rather accidentally at the beginning, which you have seen the earlier transition metals such as tantalum in a very high oxidation state, starting from a tantalum dichloride tris neopentyl species. We have seen lithium neopentyl gives you the corresponding Strock carbene version. This Strock carbene once again is nucleophilic in nature. Most importantly, Strock carbene also covers, that is Grubbs, known as Grubbs catalyst, where we have both the Strock carbene, the original Strock version and the subsequent modified version, which is nowadays are very popular in molybdenum in 6+ oxidation state. This molybdenum catalyst as well as Grubbs ruthenium based catalyst most often are widely used, and there are certain benefits of each of these two different types of Strock carbene. I would say both the Grubbs version and the Strock's own version. We do see the reactivity difference in quite a lot of cases. We will discuss this reactivity of those Fischer and the Strock catalyst, and we will get into the 2+2 and retro 2+2 and subsequent transformation to give the value added product synthesis in the next class. All right, till then keep reading. We will get back soon and we will discuss the reactivity pattern of these carbenes, mainly the Strock carbenes and the Fischer carbenes, and most importantly we will discuss also the reactivity of the Grubbs catalyst. Okay, till then, bye bye.